Hello students. In this video, I am going to talk about the angular momentum. Angular momentum is very important quantity in quantum mechanics. Now, in order to do measurement of angular momentum, you need the eigenvalue and eigenstate of angular momentum operator. So, I'm going to derive the eigenvalues of angular momentum operator using ladder operator technique, which we have already used for in the case of simple harmonic oscillator. Now, in order to use the ladder operator technique, you need some commutation relations. So in this video, I'm going to derive some important commutator relation for angular momentum. And the next video, I will calculate the eigenvalue of angular momentum. So let us proceed. So first of all, angular momentum L is can be written as R cross P. So R cross P. And now if I write in the form of component, so I can write I, J, K, X, Y, Z, P, X, P, Y, P, Z. And I can write L is ILX plus GLY plus KLZ. And this determinant I can open I, then you have X, then you can come Y, PZ minus Z, PY. Similarly, when you write the J, Y, then you can write Z, PX minus X, PZ. And similarly, you can write K, Z. So after Z, you'll get the X, and then you get after X, you will get PY, and then you get Y, PX. So everything is very cyclic nicely. So you can see, you can write now Lx value. If you want to write the Lx, so you have X here. So now I come, so after X, Y should come, and then Z should come. And then again you write Z, Py. Similarly, you want to write Y. So after Y, Z should come, and after Z, X should come. And again you write X, Pz. And similarly, if you want to write Z, after Z, X should come, after X, Y should come, and then you have a Y, Px. So this is Lx, Ly, Lz component in terms of momentum, linear momentum component, and XY, Z. Now I want some important commutator relations. Let us derive that commutation relations. So if I calculate now, say Lx, Ly. So Lx, Ly will be what? You want X, that means you want Y, Pz, then you have a Z, Py, Ly means after Y, Z should come, so Z, Px, and then you have a X, Pz. Now let us solve this one. So from commutator, I can consider this is a single quantity, and these are two quantities. So this will give me Y, Pz, commutator with this one, Z, Px minus X, Pz. Okay. And now I consider this is second quantity. So this will be Z, Py, again with a single Z, Px minus X, Pz. And now this is the two quantities, and this is a one. So now I can write Y, Pz equal to Z, Px minus Y, Pz. Minus is there. You have a X, Pz. Similarly, you can write here Z, Py, Z, Py and then you have a z px minus x pz, and then minus will become plus. So you have z py with, so I'm opening here z py with this one, sorry, this one z py with z px, and then you minus plus z py with x pz. Now we know only x px, y py, z pz do not commute x py, x pz, or y py, y pz, everything commutes. This is zero. So if you see this two here, two bracket here in the middle, here you have y pz, x pz. So y commute with pz, pz commute with pz, y commute with x. So this should give zero because there will be commutator will be zero. Similarly here, z commute with z, z commute with px, py commute with z, py commute with px, everything. So you should get zero here. And so now we left only with two pz, z. So you have a y pz and zpx here, this one, and then you have here last term, you have a zpy, and then you have a xpz, xpz. So now again here you have a pz and z do not commute, y and px they commutes. So I can consider them as a constant. I can write here y because it's coming first, and then you have a pz, z, and then you can write px here as it is. Similarly here, z pz, okay, z pz do not commute, py x commutes. Okay, so I can write because x is coming first, so I will write x here. Then you have z pz and py comes later, so I will write py here. Now you can write simply pz z. Pz z is minus iota h cross. So this comes minus iota h cross y px, and here you get plus z ps. So iota h cross x py, and now if I take iota h cross common, this gives me x py minus y px. So this is x coming, that means this is the Lz. So this is equal to iota h cross Lz. After z, x, then y, and y px. So that means Lx Ly is equal to iota h cross Lz. Similarly, we can show Ly Lz is equal to iota h cross Lx, and Lz Lx is equal to iota h cross Ly. Now, number two commutator relation, what I require is L square Lz. Okay, so if I take L square, this will give me Lx square plus Ly square. I'm writing L square. L square is your Lx square, Ly square, Lz square, and then you have Lz square, and then you have a Lz. Now I can break this one, so I can write this is the Lx square Lz plus Ly square Lz, and Lz square Lz commutes commutes because the same operator Lz square Lz. So this will become zero. So we need to solve only this one. So let us now write Lx. Okay, so this I can write Lx here. I can break Lx Lz, and then I can write Lx Lz Lx two times here, and then I can write this is a Ly, Lz, and then I can write Ly, Lz, Ly. Now, what is Lx, Lz? So Lx, Lz will give you minus iota h cross Ly. So this comes Lx, Ly. Lx again Ly minus iota h cross minus iota h cross Ly, and then you have Lx. Yz will give you Lx, so you get iota h cross Ly Lx. Again you get Lx, so iota h cross Lx Ly. So now you can see this cancels out and this cancels out, so you get 0. That means L square Lz commute. So whenever two operator commutes, that means they have a same eigenbasis. Okay, so they can have a same eigenbasis. That means simultaneous eigenstate or eigenbasis these two operator can have. Similarly, instead of Lz, there's nothing special in Lz. I can take L square Lx also. So this will give 0. L square Ly also will be 0. So L square commute with the angular momentum components. Lx, Ly, Lz, they don't commute. So that means they cannot measure simultaneously accurately. They don't have a simultaneous eigenbasis. But L square and Lz can be measured in the same basis. So this is one thing. Now I want one more commutator. Let us write now Lz, and now say we have seen L square Lz can have a same eigenstate. Now I'm defining say ladder operators. So I'm defining say L plus minus is equal to Lx plus minus iota Ly. Okay, and now we can easily show this L plus commute with L square. So this gives me L square Lx plus minus iota L square Ly, and just now we have seen these commute. So this commute with a ladder operator commute with L square. Now see what happens when we do commutation with Lz with L plus minus. So now let us do it now. So you have a Lz and then you have a Lx plus minus iota Ly. And now we can calculate say Lz Lx plus minus iota Lz Ly. Now if you have solved this one, what will come? Lz Lx will give iota h cross Ly. Okay, and you have plus minus iota here. Lz Ly order is changed, so this will give you minus iota h cross x Lx. Now if I solve this one, what will come? It will come iota h cross Ly, iota square minus 1 minus plus, so this is plus 1 h cross Lx. Okay, now if I take plus minus h cut common, so this will be Lx. Okay, plus minus so plus minus I already taken common here, so this will come plus minus iota Ly. Okay, so if I take plus h cut common, this will come Lx plus Ly. If I take minus h cut common, this will come Lx minus Ly, iota Ly. So this will become plus minus h cut, and this is your Lz. That means if you take Lz L plus this will come plus h cut Lz, and if you have Lz with L minus, you get minus h cut Lz. Okay, so we have seen some important commutators which I require for derivation of angular values of angular momentum. So in next video we'll calculate the angular eigenvalues for angular momentum without knowing its eigenstate. So I'll stop here. Thank you very much.